Okay, this is tutorial 10, and I'll share my screen here. Okay, you should be seeing the tutorial right now, and we're going to do a lot of ray diagrams in this tutorial, and so I will be handing out a copy of this homework uh, assignment. Um, the homework that goes with this tutorial, you already have the tutorial itself in that packet, but I'll hand out the one-page tutorial homework so that you can actually be careful with your drawings, and you don't have to do that on a computer screen. Now we're going to look at convex lenses, and these are converging lenses that bring the light together. And we're going to look at a very distant object through a convex lens. If we hold the lens at arm's length, we'll see a sharp image of the distant object. And we want to know, is the image formed by the lens in front of, behind, or on the surface of the lens? And we're going to use the method of parallax to find that location. And so let me uh, bring in the other camera and do that now. If we look at that vent, that stack, through this converging lens, we know that it will form a real image, and we know that that real image is going to be inverted, and then it's going to be on the other side of the lens from the actual object, that stack over there. And so that means it should end up somewhere around here, upside down. But the question is, where around here will it end up? Well, for things that are far away, and that stack is fairly far away, not as far as the mountains, but far enough, it should form an image pretty close to the focal point of this lens. And that focal point is right here, 20.8 centimeters away from the lens. So this is the setup when the stick is at the focal point, and when the stick is closer to the lens, by which I mean further away from the camera, the focal point is still back here, and this is where the image of the stack would appear. And then when we move the stick closer to the camera, further from the lens, now it would be the focal point that's further from the camera. And that's what we're going to see with the method of parallax. And then I'm going to put it back at the focal point at the end to see that they move together. And so I'm putting this wooden stick right there at that focal point, and I'm going to try to use the method of parallax that we learned about last week to verify that that is actually where the image is. Now remember, with parallax, if two objects are the same distance away, they'll look like they're moving together. And so when the camera is moved to the right, they'll both move to the right together. When the camera is moved to the left, they both move together. Now, that's not the case if the stick is not at the same location as the image. For example, if I put this stick further away from the camera than the image location, which is still back here, now the stick is further away from the camera. And so when the camera moves to the right, the stick should move to the right relative to the image. And so if you concentrate on that stack that you're seeing through the lens, and notice that when the camera moves to the left, well, the stick is moving to the left relative to the stack, so the image of the stack is moving the other way. That's what you should see. On the other hand, if I move this stick closer to the camera, then the image, which is still back here, now it's going to be the image that you see through the lens. That image is going to be moving with the camera. When the camera moves to the right, the image will move to the right of the stick. And when the camera moves to the left, the image will move to the left of the stick. And that tells us that the image is back here where they were moving together at the focal point of the lens. And there you see that the image of the stack and the stick are moving as one unit. Okay, let's go. Remember that a real image can be projected onto a screen, and so here we have this screen at the focal point, and you can see there an image, a nice sharp image of the stack that we were looking at with our method of parallax before. If I move the screen back, you see that suddenly it just becomes all fuzzy because all of the light leaving that stack is not ending up the same place on the screen. Likewise, if I move it too close to the lens, it's all fuzzy again. It's only when the screen is at just the right location that you get a nice sharp image. Okay, we found that the image of that object was on the other side of the lens, and if it was far enough away, it was at the focal plane of the lens. The lens had a focal length of 20.8 centimeters, and so if I put a screen there at 20.8 centimeters, I would get a sharp image of the very far object. Now, if we have rays coming from a very distant object, we know that in order for all of those rays to hit my little tiny lens, they all pretty much have to be coming the same direction. And so if I take that direction to be along the principal axis, then I know that the rays will converge at a point that we call the focal point. And so all of these rays that are coming in and hitting my lens are all going to go to the same location. And this is not new to you. We've been talking about this in class. And so this part of the tutorial is kind of a review. The first page of this tutorial is pretty much old news. Now, if I wanted to look at that image that was coming in, where would I put my eye? Well, if I didn't have a screen to project on, I would use the fact that all of the rays that hit the lens end up coming back together at this focal point there. And so if I look at the extremes as at the ray that just barely hits the bottom of the lens, and it's got to go like all the others through the focal point. I'm going to put that one. I'm going to put that one in red ink. Why not? Maybe. Okay. And then if I look at a ray that just barely hits the top of the lens, that's got to also go through that focal point. And I'll do that in red ink. Okay. And now we see that there's this region here between these extreme rays where I could put my eyeball, and anywhere in there I would see my real image. Now, of course, if I put a screen there, it would block that light and I couldn't see the real image from behind the screen, but I could see uh, the image projected back away from the screen. Okay. Um, so the rays were parallel to each other, and the principal axis. Principal spelled that way. Okay, now we've made the same point in class that the refraction or bending of the light due to the different media happens at the two surfaces of the lens. It is bent towards the normal when it goes into the glass and away from the normal when it goes out of the glass. But typically we avoid that mess by just saying the total bend, we can just take at the center of the a lens, even though we know that nothing bends actually at the center of the lens. It's at the surfaces. That's just make life easier on ourselves. Now, in this next part, we assume that we put a small bulb right at this focal point of our lens, and it's going to send rays in every direction. But some of those rays are going to go in the direction of the lens. And we know that we can turn back time, and if parallel rays come in and are brought to the focal point, then rays that leave the focal point are going to go through the lens and travel parallel to the principal axis. And so any ray that leaves the focal point and hits that lens is going to be refracted or bent in such a way that they come out of the lens going parallel to the principal axis, like that. Okay. And there's an infinite number of rays that hit this lens and that all be going parallel to that axis. Okay, so here we just have some name calling. The point of intersection we call the focal point. The distance between the center of the lens and that focal point we call the focal length. So this is the focal point, and this is the focal length. Now, again, this part is review. We've drawn several rays from the eraser on that pencil, and it reaches a convex lens. And we first of all consider this ray, we'll call it ray 1, and it's coming in parallel to the principal axis. So we know what it will do. It will bend in such a way that it goes through the focal point. That'd be ray 1. Now, uh, now we consider the ray that goes through the focal point on the left side. That's this ray here, we'll call ray 2. And we know that if it goes through that focal point, it is going to, uh, let's take it all the way to the center, and it's going to come out parallel to the principal axis. And so we can find the image. It will be where these two cross. And so that's going to be the image of the eraser. Okay. Now, um, we go to the next page, and we're going to consider a third ray that strikes the lens near its center where the sides of the lens are nearly parallel. Using the image location as a guide, draw the continuation of this ray through the lens and out the other side. And so if we call that lens or that ray 3, and we know that it's got to go through this image location, well, what we see is that that ray just keeps on going, keeps on keeping on. Okay. And that's a way that we can check that we have the correct image location, is that all three of those would have to go through that point. Now, if we draw the continuation of the remaining two rays on the diagram through the lens, well, we know where they end up. I mean, we don't have any special rules about where they have to go, other than the fact that we know that all of these rays, the infinite number that hit this lens from coming from the eraser, all have to go together at the image of the eraser. And so this would be, let's call it ray 4. And this one we'll call ray 5. Okay. All these rays come in and all of them come out. Okay. And you can see that if I wanted to see the eraser, the image of the eraser, I would take rays that hit the bottom of the lens and the top of the lens, and that's pretty much ray 1. And this this region here would be where I could see the eraser. Okay, and I'll just go all the way from the top. Okay. In some cases, one or more of the rays may not actually pass through the lens. However, they may still be used in determining the image location. The principal rays are only a few of the infinitely many that we might draw from one point on the object. On the diagram on the previous page, use the three principal rays from the tip of the pencil to determine the location of the image of the tip of the pencil. If possible, use a different color. Okay, so let's do that. Um, we're going to start by defining the uh, the symmetry axis of the lens. I'm just going to extend that axis out. So now when I bring the ray from the tip of the pencil that is parallel to the principal axis, you see that it doesn't actually hit the lens. But if we had a shorter pencil, it would. And we know that if we had a bigger lens, it would. And so we're going to pretend we had a bigger lens. Um, and so that ray is going to go through the focal point. And I will call that 1 prime. And then if I send a ray through the near focal point, I'm going to call that ray 2 prime. I know that it comes out on the other side of the lens parallel to the principal axis. Okay. And where those cross is going to be the image of the tip of the pencil. Now I'm just going to check my answer by putting ray 3 prime that goes right through the center of the lens. And sure enough, there we go. So now I can draw the pencil. The tip's going to be there, and the eraser's going to be there. And we've learned long before that Greg can't draw, but it's something like that. Okay. Now, this is not part of the uh, this is not part of the tutorial, but if I wanted to know where I could put my eye to see the whole pencil, the whole image of the pencil, rather, what I would do is I would, first of all, go from the bottom of the lens through the image of the tip. Oops, whoa, that was unfortunate. Okay, and then I would go from the top of the lens to that image of the tip. And I could see the image of the tip between those two red lines. Now, where could I see all of it? Well, I could see the eraser everywhere between these pencil lines, and I can see the tip everywhere between these red lines. And so that means that I would only be able to see the whole pencil in this shaded region here. And that region is going to get bigger and bigger the further I get away from the lens. But you can see that it's much more restrictive where I can see the whole pencil. There's a bigger range of where I can see just the eraser and where I can see just the tip. Okay, that was fun. Now, what if my object is closer to the lens than um, the focal point? Well, we've done this in class, so this is again a little bit of review. Um, the first principal ray comes in parallel to the principal axis and uh, goes through the focal point. I'll call that 1. Okay. Now, the second one goes through the focal point on the near side. Well, that's not possible for a ray that hits uh, the lens, and so we're going to look at a ray that uh, it looks like it's coming from the focal point. It's going in a direction as if it came from the focal point, and when that ray hits the lens, we'll call that 2, it comes off um, parallel to the principal axis. Now you see that those two rays are never going to cross, and so I'm not going to get a real image over here where all the light is brought back together. What I'm going to get instead is a location uh, behind the lens, back where the light was coming from, where the light appears to all be originating. And so if I take both of those principal rays and extend them back behind the lens, what I find is that I get something back here, and that would be the image. And if I wanted to check, I could take the ray that goes through the center of the lens, and if I send it back, it also appears to be coming from, I'll call that 3. Okay. And I've been explaining how I knew how to draw each ray. Now, we have a lens, a bulb, and a screen arranged as follows. And we saw and a sharp inverted image of the filament is going to appear on the screen when it is at the location shown. And we're going to predict how each of the following changes would affect what we see on the screen. And then we'll turn off the lights and actually do this. And I'll splice that in. We've already made that video. If we move the screen closer or further apart from the lens, well, right here was the perfect location for a nice sharp image of that filament. That's where all of the light that leaves the top of the filament and hits the lens all comes together at the bottom of the filament. So any piece of light, any ray of light, that's what we call a piece of light, that leaves the top of that filament and hits the lens is guaranteed to go at this point on the image, and likewise another ray that hits somewhere else on the lens is going to go to that same point. So there's an infinite number of these rays that hit the lens and all come together right there. Now, if I put that screen back here, well, the light that all came from a single point here is going to end up at different locations on the screen. And the same is true for all the other points of light that we consider to be sources. And so I'm going to get a very blurry, image. And that's what we'll see when we check our prediction. If I cover the top half of the lens, sometimes people think that covering the top half of the lens is going to get rid of the top half of the image. Or maybe because things get inverted, it's the bottom half of the image. I mean, who knows? But in truth, the rays that leave this top part of the lamp, there's an infinite number of them that hit the bulb. And if I cover up, I'm sorry, I misspoke. There's an infinite number of them that hit the lens. And if I cover up half of the lens, I'm only blocking half of that infinite number of rays. And if I take half of infinity, it's still a big number, okay? And so enough rays get from this point of the lamp to the screen, even with half of the lens blocked, and the same is true for light from the bottom of the lamp. So I get the whole image. I see the whole image. Now my image will be a little bit dimmer just because I've got fewer rays, half as many rays, but I will see the whole image. And indeed, we're going to find when we, actually test this, that we can cover most of the lens and still get a nice clear image, just somewhat dim. And we'll also find that it doesn't matter whether we block those rays by putting the mask in front of the lens or behind the lens. As long as there's part of that lens that's still unblocked, I'm still going to get an image. Now, we're going to splice in the other video right here to check our predictions. Okay. I'm holding an extended light source that again we can consider as a collection of a whole lot of point sources and use superposition. And we're causing the light from that extended light source to pass through this converging lens. And it's creating a real image on this screen behind the lens. And I expect a real image to be inverted, and I think we can see that that's the case. When I lift this up, the image goes down, and when I move it down, the image goes up. And but you'll notice that if I can hold it steady, I get a nice sharp image projected on the screen. which of course is another way of knowing that it's a real image, is that I can project it on a screen and there's really light there. Now, the tutorial asks us to predict what's going to happen if I move that screen closer or further away. Well, we know that at that point at the screen, we call that the focal plane, all the light that left the top of this extended source is going to end up at one point right here at the bottom of the image. And if I move the screen to some other location, maybe let's get it focused again. If I move the screen closer, it goes out of focus. There's where we had it before. If I move the screen further away, it goes out of focus again. Okay, it's only right at that one location, the focal plane, that we get it all nice and focused. Now, the second prediction we were asked to make was what's going to happen to that image if I cover up half the lens. Now, the prediction we made was that, well, the light from the top of this extended source is going out in all directions, and there are an infinite number of rays that are hitting this lens and all ending up right there at the image of the top of the extended source. And if I cover up half of those rays, I still have the other half, and half of infinity is still a pretty big number. So I predict that I'll still get exactly the same image, but that now it will be dimmer. And sure enough, that's what I see. And it shouldn't matter whether I cover up the front, put it in front of the lens or behind the lens. I still get the image, the whole image, but just dimmer. Now you see there I've covered up most of the lens, but I still get all of the image. Now, if the screen were removed, would we still be able to see an image of the bulb? Well, yeah, we did that with the remember the vent, the stack on the building next door. Uh, we we found that we could either project that onto a screen, or we could actually just see it by putting our eye in a place where the light was um, spreading out. So the answer is yes, but does it matter where your eye is located? Well, that's also a big yes. Again, we have to look at the extremes of the lens, um, like we did here. We found that if we look at a, a ray that leaves the bottom of the lens and a ray that leaves the top of the lens, we've got to be somewhere in this cone right here, looking back in the direction that the rays are coming from in order to see that image. Okay, that's the tutorial. I'm going to stop the share. Okay. And I'm going to stop recording.